Hello, everybody. So welcome again to this technical session of DigiShape. These are some sessions that we are doing every 2 weeks where we find the participants around the Netherlands, both practitioners and academics, to share their experiences with different approaches to digital, let's say, digitalization of the water sector. And today we're going to have a really nice presentation. So today we have a presentation by Taj de Vries. Yes, did I pronounce it correct?
Yeah, very good.
So Taj is an advisor at Nelen Schuurmans. And yes, that's also correct, Taj? Sorry?
Yeah.
And today he's going to present a really nice work regarding the determination of water levels by applying algorithms on remote sensing data. So we're going to have his presentation and then we're going to have some space for questions. And please, the floor is yours.
So yeah, my name is Taj de Vries. I recently started working at Nelen Schuurmans, and this is one of the first projects that Thomas invited me to. So normally you probably see Thomas Berends at these sessions. He works partly at the TU Delft and partly at Nelen Schuurmans, but today we have to do with me. And I'm going to tell you something about the work we did on determination of water, applying algorithms on remote sensing data. So the agenda for today, I'm going to give you some problem description that probably water boards and other instances have with determining water levels, the goal of the project we are aiming for, the data inventory we have so far, the methods we applied, first results we got, and some conclusion and the further development we're aiming for with this project. So within the DigiShape universe, we are cooperating with the following instances, and they are providing us with the data we're using. And first, the problem statement. The Netherlands consists of a vast number of waterways, and each of these waterways have a legally established target. In the picture on the right, we can see an area near Purmerend, and every shape has a certain water level it has to meet by law. And these assessment is mostly done at this time by using water level measurement at pumping stations or by hand, which is a lot of labor intensive process. And only 700 out of the 2600 water levels are measured in the water board of the Hoogheemraadschap Noorderkwartier. And this is a very large problem. So we need to assess the opportunity of digitalizing the LiDAR data that is accessible, because in the recent future, the use of remote sensing data has become very much more available. The most common example is, of course, the actueel hoogtestand Nederland, where every some years the dam is measured, but also for Hoogheemraadschap Noorderkwartier is the assessment of dike with LiDAR data. So they are measuring the dams of dike and trying to assess if there are cracks in the dikes, but at the same time, they're producing a byproduct. They are measuring water levels. What we want to do is assess the data, see if we can make something of the byproduct of these LiDAR data. So the goals. The opportunities of the byproduct. There is a large amount of data that is being measured, and it's very hard to process. LiDAR data, and there are very large files. They require some technical knowledge to process. And we want to enrich the data. And last, we want to make an easy and accessible method for these water boards and Rijkswaterstaat so that they can just use this method to enrich their data themselves. So far, we have gotten data from some instances, and these are all remote sensing data. They come in loss or loss with an S or loss with a Z file. It's just the difference between compiled or not compiled files. And And a good thing to know is that we haven't processed all the data yet. The ANR is obviously a very, very large data set, so that it's very hard to process. And the Rijkswaterstaat data we only got recently. So we'll be focusing on two cases. One is from the weather skip, where they measured some dam, and we are trying to measure the water levels out of it, and the data from Hoogheemraadschap Noorderkwartier near Purmerend, which I mentioned before. Okay, so now we have loss files, but we also want to process them to water levels. So what do we do? Well, the method is in essence very simple. We have a point cloud. We want to know every point that is within our shapes of the water. And we want to say something about the shape and the point cloud data that we are left with. So how do we do this? So first we get all the shape files, which for now we use the PGT waterdelen, so it's the basisregistratie of all the waterdelen, and we filter out all the points that are within the waterdelen. For this we are using something that's called the STR tree, which makes all this indexes the geometries that are within the shape files and initializes a tree. Within this tree, it is very, very easy for the algorithms to find points, which are also geometries that are within the shapefile geometries. And for the trees, we initialize two separate trees. One is the water bodies, that are the PGT waterdelen, and the second one is peilgebieden, or fixed level drainage areas, which is the legally established water level that the water board has to apply. Next, we use a very simple algorithm. We just loop through all the points that are within our loss file and ask the script, okay, is this point within our geometry? No, then we discard the point. If it is, then we store the information. And also within this loop, we query to the second tree, where we store the information of the fixed target level. And we also use the row-wise dependency of Python itself, because querying from pandas or NumPy is far slower. So what we are left with is all the points within the shapefiles. But still, as everyone probably knows, there's still a lot of noise that remains. There are trees and bridges that are not filtered or can be above the shapefiles of the PGT. So we need further filtering. And this filtering is very dependent on the location and the thing we want to know. So in rivers, there probably won't be a lot of trees, but in small waterways, such as here in Purmerend and what we see here from the Hoogheemraadschap Noorderkwartier, there's a lot of noise. So we present different methods for assessing the point cloud that we are left with. And we present three methods, so the user can choose one of the methods that he thinks is appropriate or compare the different methods. So the first one we call vertical slicing. So every peilgebied that we have has a legally established water level. And what we do, we take a vertical margin from the fixed drainage water level, and we just create an upper and lower limit for it. And then we filter out all the points that are not within this limit. So what we are left is only the points that lie within the vertical margin we defined. Secondly, we have the model value. So what we do, we preemptively create a raster of, in this sense, 1 by 1 raster cells, and we create a value distribution for all the points that are within this raster cell. Then we can take the model, the mean, or any value you want from within this raster cell, and just create digital elevation model from the model mean value. The third method is that we can just create a polygon and only want to filter points that are within the polygon. This is especially handy if you don't want to process all the data at once, but just want to get a sense of some points in your waterway or an area. And what we do is create a polygon and then filter points out like we did before the initial filtering, and we create statistics about this polygon that we have made. So now we have 3 methods of accessing data, and we will go to some initial results that we've had. And we first come to a very bad case, a very bad result. And that was in the waterboard of Letterscape. What we see here is that there are large data gaps because that is a couple of reasons. One, there's a lower point intensity, so lower point with a lower chance of reflecting points, and that the type of LiDAR that was used has a low reflection of water. So we see large data gaps because at some point the laser just doesn't reflect back to the device and we don't get data. Another problem is that the data collection wasn't stored by Weatherscape, so we couldn't compare it to the actual measured water level. And then we go to the Hoogheemraadschap Noorderkwartier. And what we see here is that they have data with a lot of point cloud density, and that the data that was measured is also very good at creating a digital elevation. And what we also have is measurements from pumping stations that are very near the elevation that we measured with the LiDAR. So So what we can do here is compare the measured water levels at the pumping stations and the water levels with the different methods that we applied. And we only use the first 2 methods because they apply to the whole raster that we made, and the third method would only be a single point on the dam that we are showing, which is a lower statistical significance and is very deterministic in our opinion. And what we see is that there are very promising results. So at the fixed range level, that is the legally established level, that is not especially the level we measured. So that is in the first row, that is the measurement. So what we see is that we are very capable of determining the water level within a difference of 2.5 centimeters. This is very promising because for Hoogheemraads Noord, for Hoogheemraads for H, and K, they are of course interested in the water level itself, but they are also very interested in large differences. So differences here are very small, but if our differences are very large, like 50 centimeters, they also want to know. And if there's such a difference, they can obtain it with the DEM of the LiDAR data that we processed here. These are the initial results, and these are like the pumping stations that we could compare it with so far. Then we go to a discussion. So what we saw is that the quality of the produced raster is very dependent on the data we had. So the Weatherscape is very poor data, so we're not able to create a very good digital elevation model of the water level, and that the method is very situation dependent. If there are a lot of noise in the data, you might want to do the vertical slicing first, but when there's not a lot of noise in the data. So maybe at a lake or a river, you do not have to do vertical slicing as well. What's also very important is that with this large file, the method is still relatively slow. So we are optimizing the script still, and that probably will take some time. So yeah, that is something we have to deal with right now. And if we look at the methods, okay, so if we look at method 1, the vertical slicing, it's very deterministic. So now if I go back to this, so for now we took a vertical margin of 0.1 meters from the fixed drainage water level. So every point outside of the vertical margin is not used for measuring the water level. So in that sense, so if the water level lies outside our vertical margin, we're not able to measure. And that's also, that's not very neat and can be better, but we are very good at measuring the water level itself. And that's why we are not able to catch deviation. For method 2, we are not able to catch skewness in the data. So if the modal value does not represent the actual value or the mean value of the data very well, then we skew to some modal value. And the problem is that noise remains in the data because we don't apply vertical slicing. And we didn't use method 3 because it has a low statistical value. We're only measuring the water levels at one location, and the water level can of course differ along the line of a lake or a river or every waterway. So what we want to do is further develop the method, and what we really want to do is make it very easy, accessible for waterboards and other instances. So we want to make a stepwise program. So first, what we do is we have a data inventory. What we saw was the loss files and the shape files. Then we go to step 2, which is only an initial filtering. So we filter out all the points that are within the shape files that we've met. Then we are left with a data set that is stored, and we can use this data set for all kinds of things, and we can apply the method for filtering that we want. So we go to step 3. We can apply some filtering that we want, and you can also add your own filtering methods to it. And then in step 4, we want to assess the results. So get mean values, or we can compare them to water levels that we measured. And in this way, we can use data that is already available, like the AHN, or what we see at Hoogheemraadschap Noorderkwartier, that they are using their own LiDAR data for measuring dike levels, and enrich it and use it for other purposes that we did not do before. And also already talked about, we still need to optimize the scripting process because it's still very slow, and at this rate it takes a very long time to process very little data, and that's not something that is, we want to have a quick assessment of the data that we obtained. So in conclusion, we have very good initial results, but they're very dependent on the input data. There's still a lot of room for further development, but we think we can use the data that we've had so far and make a difference for measuring the water levels in very small waterways that are not measured at all right now. And what we can do, this method is also applicable not for water levels only, but you can use every polygon or shape that you want and assess what you want. You can also measure roads, or if you measure the dam of roads, or maybe the dam of trees you have, and see if so it's very generally applicable right now. So that was my presentation. I hope you enjoyed it, and you can ask questions right now.